perform a ground fault calculation using a raceway as an equipment ground, firstly determine the raceway resistance. Find the resistance value of the raceway per unit length, typically ohms per foot or meter. This information can be found in conduit manufacturer catalogs or by contacting an electrical supplier. Calculate the total resistance of the raceway by multiplying the unit resistance by the length of the raceway. Secondly, determine the fault current. Use the fault current protection device rating, such as a circuit breaker or fuse, to determine the maximum fault current that can flow through the ground fault. Thirdly, calculate the ground fault potential, abbreviated as volts GF. Volts GF equals fault current multiplied by raceway resistance. Fourthly, determine the touch voltage, abbreviated as volts T. Volts T equals volts GF multiplied by contact resistance. Contact resistance is the resistance between the touch point and the equipment ground. It depends on factors such as soil conditions, moisture level, and materials of the touch point. For most calculations, a conservative value of 25 ohms is typically used. As an example calculation, consider a raceway of 100 feet of 1/2 inch EMT conduit with a raceway resistance of 0.2 ohms per foot. The total raceway resistance, represented as R, is calculated as 0.2 ohms per foot multiplied by 100 feet, equaling 2 ohms. If the fault current is 1000 amps, the ground fault potential, volts GF, is calculated as 1000 amps multiplied by 2 ohms, resulting in 2000 volts. The touch voltage, volts T, is then calculated as 2000 volts multiplied by 25 ohms, which equals 50,000 volts. To find resistance properties of conduits, conduit resistance data can be found in the National Electrical Code, manufacturer catalogs, or online resources. The NEC provides tables with resistance values for various types of conduits, including metal, plastic, and flexible conduits. Manufacturer catalogs often include resistance data for specific conduit types and sizes. Online resources can provide resistance values for different conduit materials and dimensions. Let's further elaborate on the key aspects of ground fault calculations when using raceways as equipment grounding conductors. Firstly, understanding the importance of accurate resistance measurements is crucial. The resistance of the raceway directly impacts the magnitude of the ground fault current and the resulting touch voltage. Inaccurate resistance values can lead to underestimation of the potential hazards and compromise the effectiveness of the grounding system. Therefore, it's essential to utilize reliable sources for resistance data, such as manufacturer specifications or the National Electrical Code, and to ensure that the measurements are appropriate for the specific type and size of raceway being used. Secondly, the role of the overcurrent protection device cannot be overstated. The overcurrent protection device, whether a circuit breaker or a fuse, is responsible for interrupting the flow of fault current in the event of a ground fault. The device's current rating and its stripping characteristics determine the maximum fault current that the raceway will be subjected to. It's essential to select an overcurrent protection device with an appropriate rating to effectively protect the equipment and personnel from the hazards of ground faults. Thirdly, the concept of touch voltage warrants further discussion. Touch voltage is the potential difference that a person could be exposed to if they were to come into contact with an energized surface during a ground fault. The magnitude of the touch voltage is directly related to the ground fault potential and the contact resistance between the person and the equipment ground. The lower the contact resistance, the higher the touch voltage. Therefore, it's important to minimize contact resistance through proper grounding practices and the use of insulating materials. Fourthly, the contact resistance of 25 ohms is a commonly used conservative value for ground fault calculations, but it's important to recognize that the actual contact resistance can vary depending on several factors. Soil conditions, such as moisture content and composition, can significantly affect contact resistance. Dry soils tend to have higher contact resistance than moist soils. Similarly, the type of material that a person is in contact with can influence contact resistance. Insulating materials, such as rubber or plastic, will have higher contact resistance than conductive materials, such as metal. In situations where the actual contact resistance is known to be significantly different from 25 ohms, it's important to use the appropriate value to ensure accurate ground fault calculations. Fifthly, the selection of the appropriate type of raceway for the application is a critical consideration. Different types of raceways have different resistance characteristics and may be more or less suitable for use as equipment grounding conductors. Metal raceways, such as ENT and rigid metal conduit, typically have lower resistance than non-metallic raceways, such as PVC conduit. This makes metal raceways generally more effective as equipment grounding conductors, as they provide a lower impedance path for fault current to flow back to the source. However, non-metallic raceways may be preferred in certain applications where corrosion resistance is a primary concern. Sixthly, the length of the raceway is a significant factor in determining its total resistance. As the length of the raceway increases, the total resistance also increases. This is because the resistance of the raceway is directly proportional to its length. Therefore, it's important to keep raceway lengths as short as possible to minimize the overall resistance of the grounding system. In situations where long raceway runs are unavoidable, it may be necessary to use larger sized raceways to reduce the resistance per unit length. Seventhly, the use of supplementary grounding electrodes can enhance the effectiveness of the grounding system. Grounding electrodes, such as ground rods or ground plates, provide a direct connection to the earth and help to dissipate fault current into the ground. This can reduce the ground fault potential and the touch voltage, improving the safety of the electrical system. The NEC specifies requirements for the installation and sizing of grounding electrodes, and it's important to comply with these requirements to ensure proper grounding. Eighthly, the concept of impedance should be understood. While the example calculation focuses on resistance, impedance, which includes both resistance and reactance, is the more accurate measure for alternating current circuits. Reactance is caused by the inductance of the raceway. This is especially important in longer raceway runs or when dealing with high-frequency ground faults. Ninthly, consider the effect of parallel grounding paths. In many electrical installations, there may be multiple grounding paths available for fault current to flow. For example, in addition to the raceway, there may be a separate equipment grounding conductor running alongside the circuit conductors. When multiple grounding paths are present, the fault current will divide between the paths based on their relative impedances. This can reduce the amount of fault current flowing through the raceway and lower the ground fault potential. However, it's important to ensure that all grounding paths are properly sized and installed to handle the available fault current. Tenthly, regularly inspecting and testing the grounding system is essential for maintaining its effectiveness. Over time, connections can loosen, corrosion can occur, and grounding electrodes can deteriorate. These factors can increase the resistance of the grounding system and compromise its ability to protect against ground faults. Regular inspections and testing can identify these issues and allow for corrective action to be taken. The NEC recommends periodic testing of grounding systems to ensure that they meet the required performance standards. The grounding system is designed to provide a low impedance path for fault current to return to the source, which facilitates the rapid operation of overcurrent protection devices such as circuit breakers or fuses. Without a properly functioning grounding system, fault current may not be sufficient to trip these devices, resulting in prolonged exposure to dangerous voltage levels and increasing the risk of electrical shock or fire. Understanding the principles of ground fault protection and how to perform ground fault calculations is therefore essential for electrical engineers, electricians, and anyone involved in the design, installation, or maintenance of electrical systems. The NEC serves as a comprehensive guide for safe electrical practices and provides detailed requirements for grounding and bonding. Adhering to these requirements is critical for ensuring the safety of electrical installations and preventing electrical hazards. Ground fault circuit interrupters, abbreviated as GFCIs, are another important component of ground fault protection. GFCIs are designed to detect even small amounts of ground fault current, typically in the milliamp range, and quickly interrupt the circuit to prevent electrical shock. GFCIs are commonly used in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. While GFCIs provide excellent protection against electrical shock, they do not necessarily protect against all types of ground faults. In some cases, a ground fault may occur without tripping the GFCI, particularly if the fault current is below the GFCI's tripping threshold. Therefore, it is important to have a comprehensive ground fault protection strategy that includes both grounding and GFCI protection. Electrical safety is a shared responsibility, and it is important for everyone to be aware of the potential hazards associated with electricity and to take steps to protect themselves and others. By understanding the principles of ground fault protection and following safe electrical practices, we can create a safer environment for ourselves and our communities. Remember, working with electricity can be dangerous, and it is always best to consult with a qualified electrician if you have any questions or concerns. The information provided in this narration is intended for educational purposes only and should not be considered a substitute for professional advice. Always follow the NEC and other applicable codes and standards when working with electrical systems. Grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to return to the source, while bonding connects all metal parts of an electrical system together to create a common ground potential. This helps to prevent voltage differences between metal parts, which can cause electrical shock. The NEC provides detailed requirements for grounding and bonding, and it is important to comply with these requirements to ensure a safe electrical installation. Some additional points to consider are: firstly, always to energize the circuit before working on it. This is the most important safety precaution you can take when working with electricity. Use a voltage tester to verify that the circuit is de-energized before touching any wires or components. Secondly, wear appropriate personal protective equipment, abbreviated as PPE, such as safety glasses, gloves, and insulated footwear. This will help to protect you from electrical shock and other hazards. Thirdly, never work alone. Always have someone nearby who can assist you in case of an emergency. Fourthly, if you are not comfortable working with electricity, hire a qualified electrician. It is better to be safe than sorry. When performing ground fault calculations, it is important to use accurate information and to follow a systematic approach. The steps outlined in this narration can help you to perform these calculations correctly and to ensure the safety of electrical systems. Remember, electrical safety is everyone's responsibility, and it is important to take it seriously.